Okay, so let's get started. Today we're going to work on this thing called prime factorization. So remember, this is where I said we'd start tomorrow, yesterday. So let's erase this. And what page is it? Page 8, right down in the corner there, page 8. And we are working on this thing called prime factorization. So I'll start at the bottom of the page. Prime factorization. When finding the square root or cube root, you can use the process of prime factorization. So what is prime factorization? Okay. All numbers can be expressed as a product of primes. All numbers can be expressed as a product of primes. Some examples of primes. Okay, what's a prime? Like 7. What's interesting about 7? It can only, primes only divide by 1 and itself. And perfectly, yeah. Like, you can divide any number, obviously you can get decimals, but to get a whole number, you can only be divided by 1 and itself. And he said 7. 7, a lot of people remember 7 for some reason. So, what are all the prime numbers? So we'll just go in order. 1 is not prime. The first prime is 2. And it's the most weird prime because it's the only one that's even. Okay? The next prime is 3. The next prime is good. The next prime is, now there's no chance they'll ever be even, so don't ever check even numbers. So next after 6 would be 7 works. Check it, no, 9. 3 times 3 is 9, you guys. So not 10, 11, 13, 15, no, 15 divides by 5, 16, 17, 18 is even, 19, 20, 21, not 21, 23, 25, no, divides by 5, 27, no, divides by 3, 29, yeah, 31, and the list goes on forever. There's an infinite amount of primes. You'll always can find another prime, dot, dot, dot. Some examples of numbers which are not prime, 4, 6, basically any even, like 9, 15, not prime. 1, good, 1's not prime. Excellent. The reason 1's not prime is because, like, 1 is special. They call it the identity. Like, is about uniqueness. Yeah, it doesn't really matter. There can only be one Highlander. Okay, so, and let's just explain this a bit. You know, in chemistry, like, I put this like this. What is this in chemistry? Water. And we call this a compound. Okay, what are all compounds made up of? Elements. Is there anything more basic than an element? I mean, other than like atoms, or like, other than like protons and neutrons and stuff. Is there any more basic thing than an element? No. And all compounds are made up of elements. So that's chemistry, science, but in math, the compounds are called composites, and the elements are called primes. All composites are made up of primes. So let's think of a number that's not prime, 12. How would we break down 12 into its primes? how would we break down water into its elements? How do we break down 12 into its primes? Okay, so 4 times 3. And then 4 could be broken down into 2 times 2. And 3 is still 3 because 3 is prime. So 2 times 2 times 3. 12 is 2 squared times 3. Because there's 2 2's and 1 3. So 12 is 2 squared times 3. Want to try another one? Like let's try 14. What would 14 be? 7 and 2. So that's it. 7 and 2 are both primes. So 14 is 2 times 7. That's it. And I always just put the primes in their order from smallest to biggest. Let's try another one, like 30. 30 could be broken down like 5 times 6. 6 is not prime, so keep breaking down 6. 6 is 2 and 3. So then 30 would be the same as, and in order, 2 times 3 times 5. Let's try 20. What would 20 be? How can you break down 20? 2 times 10, good. And then how does 10 break down? 2 times 5. So how would we write 20? 2 times 2 times 5, so 2 squared, because there's 2 2's and 1 5. So 2 squared times 5. So what we can do here, if you think back to last day, we're talking about perfect squares and perfect cubes. If we want to be able to identify a perfect square or perfect cube by hand, we have to use prime factorization. They want us to try 729. So, 729. What does it divide by? Why are you using 3? You have good intuition. Always start with the smallest possible prime. Start with 2. Is it even? So don't try 2. If it's even, start with 2. If it's even, start with 2. Odd, start with 3. Okay? And then it, so divide 729 by 3 in your calculator, and what do you get? 343, I think. 247? 243? 243. 3 is prime, move on to the 243. This is also odd. Start with 3. Divide by 3, what do you get? 81. Continue on with 81. It's still odd. You could, but let's just use primes. Always just use primes. 27. Keep going on 27. 9. Divide by 3 again, you get 9. Go on 9, you got 3 and 3. Now you're done. It's not unnecessary. All right, now, how would we write 729? How many 3's are there? 6. So the index is 6. 6 is an interesting number because you can group 6 into pairs. And 6 is also an interesting number because you can group 6 into triplets. So where am I going with this? Pairs and triplets. Think about index. Powers, perfect cubes, and perfect squares. So is 729 a perfect cube? Yes, because there's perfect triplets. Is it a perfect square? Yes, because there's perfect pairs. Let's take a look at some of the ones we did over here. Is 12 a perfect square? No. Why? Because there's a pair of 2's, but there's just a single 3 kind of hanging around dangling. It doesn't pair up, so it's not a perfect square. There's no triplets, so there's no chance it's a cube. What about 14? Is there pairs? No, 14's not a perfect square or a perfect cube. What about 20? There's a pair, but then 5 is just dangling. So is 20 a perfect square? No. What are the perfect squares? Let's think. Yell one out. 100. What does it break into? 10 and 10. What does 10 break into? 2 and 5. 2 and 5. So there's a pair of 2's and there's a pair of 5's. Perfect pairs. Nothing dangling on the side. So is 100 a perfect square? Yes. What would 1,000 do? 1,000 would have another 10 there, and there would be another 2 and 5. So now you'd have triplets. 3 2's and 3 5's. So it's all about the primes. Chris, you alive? All right. Okay, so creating a factor tree helps to organize the prime factors. Prime factors are only divided by 1 and itself. Okay? I don't typically use the factor tree. I use this thing called a division table, but you can do either. Oh, 3 methods to determine square or cube roots. Well, basically calculator or prime factorization. I know 2. I don't know why there's 3. You look at your calculator, if you type it in and you don't get a perfect whole number, it's not a perfect cube or a perfect square. So you could totally cheat with your calculator, but if they ever said you have to do it by algebra, you have to do prime factorization. So if the test ever said algebra show, you'd have to do prime factorization. Okay, so use prime factorization to determine whether the following numbers are perfect squares, perfect cubes, or both. So let's do 144. Do we all know 144? It's question. Yep. 12 times 12. So right there you know it's a perfect square because there's a pair of 12s. Okay, but let's just keep going. 12 would break into 6 and 2 or 3 and 4, whatever you want. 3 is just 3, 4 is 2 and 2, 3 is just 3, and 4 is 2 and 2. So how could we write 144? 144 is equal to, yeah, do it in order. So 2 goes first. How many 2's are there? 4. And how many 3's are there? 2. Look at those those indices. Can 4 and 2 be grouped into pairs? Yes. So here's a pair of 2's, here's a pair of 2's, and here's a pair of 3's. You like that? All right, now I'll show you the division table for the next one, 216. This is the division table. So what's the strategy with prime factorization? What do you always start with? The smallest primes. Okay, so always start with smallest primes. So 2 and 3, right? Those are your starts, 2 and 3. If it's even, go after 2. If it's odd, go after 3. 216 is even. So start with 2. Put 2 on the side. Divide by 2. What's the next number you get? 108. That's also even. Keep dividing by 2. Then you get 56. It's 56. It's 56. It's 56. It's definitely 54. Keep dividing by 2. You ever have someone like that, just so stubborn? No. Okay. 27. Now 27's odd. So then now we'll start with 3. 3 works. What if you try 3, you type 27 divided by 3 and then you get a random decimal? Then that one doesn't work and then move on to the next one. Does that make sense? So 27, we already did 27. It becomes 9. Divide by 3 again, you get 3. Divide by 3 again, and you get 1. Once you're at 1, now you know you can stop. And these are all the primes. There's a triplet of primes, and there's a triplet of 3s. So this is a perfect square or a perfect cube? Cube. And what is the, do you guys know this one? Do you remember? 216, the cube of 2, oh Jesus. Pardon me, I took the Lord's name in vain. You go, cube root of 216 is, put this in your calculator. Do you guys know this one? No. 6. So why is it 6? What's the, for this triplet, just take one of them. For this triplet, take one of them. What's 2 times 3? 6. Yeah, that's because it's all based on primes. All right. This stuff, we're going to move on because we already know this stuff. I'm going to let you guys do this on your own. So take your own on your own. You can use a calculator, or you can use prime factorization. You might want to do this on the side. I'll do one with you, okay? Let's do 4096 together. Okay? I'll do one with you. 4096. What do you guys like, the division table or the factor tree? Factor tree? Okay, so let's use the factor tree. What do you always start with? Lowest prime. Is it even? So let's go with 2. This one would be 2048. Oh, I know these ones. These are the multiples of 2. This is going to be divisible by 2 the whole way. Next one is 24. If you're a computer science kind of person, these should be jumping out at you right now. Keep going. 512. Ever get like megabytes of RAM? What are their numbers always? What's the next one? Oh, 256. Keep going. 128. Oh, keep going. Oh, that's like the Nintendo 64. Keep going. 32. That's like PlayStation 1. Oh, that's like Super Nintendo. Yeah, it's the bits and bytes for computers. It's all based on powers of 2, binary. 8. Oh, NES. The first amazing system, NES, for me. 8-bit. You guys ever hear 8-bit? There it is. 2 and 4, and then finally 2 and 2. How many is that? Oh my gosh.
2 bits, that's your palm.
That's your palm. Yeah, I prefer the division table, personally. Okay, so how many were there? 4096 is equal to how many 2s? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Did I miss? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12. So the index is 12. How can 12 be broken down? Can it be grouped into pairs? Yeah. So 4096 is a perfect square. Okay, you could take the square root of 4096 and you'd get a perfect whole number. Can you put 12 into triplets? Yes. Groups of 3? Yes. So 4096 is also a perfect cube. It's both. Okay? So let's put them into pairs. 1, 2, 3, 4, 5, 6. So what's 2 to the 6? 64. What's 64 times 64? 4096. Let's put them into triplets. 1, 2, 3, 4. What's 2 to the 4? 16. What's the cube root of 4096? 16. And then later we'll learn that basically you just take the index, divide by 2, that's the perfect square, the square root. Take the index, divide by 3, and then that power will give you the perfect cube. Okay? So here's the assignment for this section, and I need to bring up one more document. So I'm going to pause the recording, and I'm going to hand something out to you. Okay, so here we go. I want you to try to write 48 and 72 as a product of primes. This is called prime factorization. You have two choices. You can use a factor tree, or you can use a division table. So do this now and then double check with me as you work. What's up, Jack? Alright, so I'm complete. I did it two different ways. You can look at the board whenever you're ready. The one thing that I really want you to try is to write it as a expression of primes with powers, because that is the unit we're in. This is roots and powers, okay? So it's basically like, it's no different, like if you've taken Science 10, it's no different than how we use the symbols in chemistry, okay? There's two H's and one O. There's 3 2's and there's 2 3's. It's just an index of a symbol. Same with H2O, just an index of a symbol. It tells you how to read in that that discipline. Okay. All right. Does everybody have this? All right. Okay. So in this booklet, if you look at the title of the booklet, it says application of prime factors. So we're going to have two applications. There are going to be GCF, LCM. There's two applications of primes. Greatest common factor and lowest common multiple. Good. We are going to use greatest common factors a lot, especially in the next unit, factors and products. And we're going to use LCM if for one particular type of problem. But LCM is used when you add fractions. You know how you need to get the lowest common denominator? That's what LCM is. So, yeah, like when we start doing powers that have fractions, fraction powers, it's kind of weird. So greatest common factor, like 6 has factors 2 and 3. And multiples is like the multiples of 6 would be 6, 12, 18, 24, and so on. Does anybody know the difference between factors and multiples? Don't get them confused. Kalela, are you paying attention? What is that thing? Oh my gosh, Kalela, go put it on my desk. Alright. So, the first one, greatest common factor. Use prime factorization to determine the greatest common factor. Alright. This is where the division table whoops the factor tree's butt. Because you're going to do it at the same time. So what's the greatest common factor of two numbers? So what's the factor that's in common that's the greatest? Well, if we do prime factorization of both at the same time, we'll pull out common factors to the left. So common factors to the left, just like Beyonce. So 90 and 225. What do we always start with? The lowest primes. Are they both even? Are they both odd? So we got to skip 2 and 3. We got to jump into 5. Why 5? Because it ends in 0 or 5. For sure 5 works. If it ends in a 0 or 5, 5 works. Like 5, 10, 15, 20. It's always 5 or 0. Divide each of them by 5, you get 18 and 45. Yeah, so something is really kind of wigging me out here. I think 3 still works. So maybe you should always just check 3. And you don't always have to check 2, because if one of them's odd, 2 won't work. So I think always just check 3. And I would go in order. I would go 3, check it. Then 5, check it. And then 7, then check. Okay, and so on. Just check them in order. That way if you skip one, you're like, "Oh, did I do that one?" It's like you'll never miss it if you always go in order. So try 3, 6, and 15. Looks like you could do 3 again. You get 2 and 5. Is there anything in common that I can pull out in 2 and 5? No. So what are the common factors? 2 3s and a 5. Those are the common factors. Okay? So write this down. Common factors for 90 and 225 are 3 and 5. But the greatest common factor is 3 squared times 5. The greatest common factor is the product of all the numbers you've pulled out to the side. That's super easy to remember. All the ones that are on the left, like Beyonce, are the greatest common factor. Okay, Beyonce is the queen bee, the biggest queen, the biggest whatever. GCF, biggest factor, easy way to remember it. Pull it to the left. Okay, easy way to remember. Queen bee. So 3 squared times 5 is 9 times 5 is 45. 45 is the biggest number that divides 90 and 225 perfectly. Does that make sense? Okay, 154, 198 into the division table. They're both even. Divide by 2. Chase, are you clicking or? Oh my gosh. Can you go put that on my desk? Oh, I think the rules are different for you. He's above the law. I love it. 77 and 99. Thank you. Now 77 and 99, these ones should be jumping out at you because they repeat. 77, 99. So they divide by the prime number, that is 11. 11, and then you get 7 and 9. So 7 is prime, so you definitely have nothing in common with 9. Okay, even though 9 can still be broken down further, we don't, because there's nothing in common between 7 and 9. So the common factors are on the left here, 2 and 11. The greatest common factor is 2 times 11. Okay? And the proper way of writing this would be like this, actually. Oh my gosh. Not like that. The proper way of writing this would be like this. It would be GCF bracket 154, comma 198, comma equals 22. And the TI, the Texas Instruments calculator, will be able to find a GCF for you, just like this. As long as it's only two numbers.
Their GCF button.
Yeah, it's in the catalog. Second 0.
Oh my.
And then it prompts you. Second 0. And then it prompts you with alpha. So click G, find G in blue. And then scroll down until you find GCD. And then when you enter it, you have to use a comma, which is down right there. Alright, so moving along, that's GCF. Okay? You need to know how to do GCF. It's going to be on your daily quiz tomorrow. Okay, those are really big. Now we can jump into LCM.
Greatest common.
LCM. Okay, so let's take a look at LCM. Okay, here's LCM. This is how you would do it in elementary school. Like my son, whenever he comes home, I'm like, what'd you do in school today? He's like, patterns. And then like the next day, I'm like, what'd you do in math today? He's like, patterns. And then like a month later, I'm like, what'd you do in math today? He'd be like, patterns. I'm like, man, is that all you do? But boy, oh boy, can that boy skip count. He can skip count like no other. 6, 12, 18, 20. He can do this like the back of his hand, like no problem. Okay? So these are multiples. Where, guys, is the lowest common multiple? Where do they match up for the first time? So the LCM of 6 and 8 is 24. How the heck do you do that with primes? Let's try it. Yeah, we skip a page. We skipped a page, yep. Okay, 6 and 8. Our goal is to be able to do this, not like they do in elementary school with the lists, but with the primes. So 6 and 8, is there a prime in common? 2. Then you get 3 and 4. Okay. Remember when I told you on the last one to only pull out the common ones? Well, with the multiple LCM ones, you just keep pulling out primes till you're done. So 3 and 4, well, 3's already prime, so don't worry about 3. Just drop 3 down to the next one. Don't worry about 3. What about 4? Can you pull a prime out of 4? 2. And then this becomes 2. Okay. Actually, I want to erase that arrow. Erase that arrow. Because you only drop down the arrow on the ones that are already prime. If they're already prime, just drop it to the next one. You don't care about it anymore. So I took a 2 out of the 4. Now, we need to make sure we get 24. Does anybody see it? 2 times 2 times 3 times 2. What is that? Whoops. Yeah, what are the product of all these primes? 24. So for this one, you make an L for LCM. Ho, ho, ho. Okay? So remember, queen B out to the left, and LCM, make a L. Can you guys remember that? Okay, let's try some of these. Okay. 15, 35. We just gotta keep, for LCM, pull out primes till you're done. And then you make L. So what prime is in common for 15, 35? 5. Then you get 3 and 7. Those are all primes, right? 3, 5, and 7 are all primes. So we're done. Now you make the L. So the LCM for these guys is just 3 times 5 times 7. LCM of 15 and 35 will equal 3 times 5 times 7. 105. Alright, let's try the next one. 1, 2, 6, 4, 4, 1. Okay, you can't use 2 because 4, 4, 1 is odd. So you try 3. Divide each of them by 3. What do you get? Do they both work? You both get perfect whole numbers? Okay, so we can use 3. The numbers are 147. Try 3 again. 42 works. Does 147 divide by 3? It does? So 3 works again. The numbers are 14 and 49. Yeah, you 7 pops out at you because 14 would become 2, 49 would become 7. Now you make the L. So the LCM of 126 and 441 would equal 2 times 3 squared times 7 squared. Whatever that is. What is it? 2646. Alright, I'm a little bit nervous, so I need to double check. Oh, we have a discrepancy? That number was wrong?
882.
What's up with my screen? Oh my gosh. Okay, so the LCM was 882? Okay, so let's fix that. Okay, now what I want to show you, this is what I want to show you. Alright guys, let's take a look at my screen. Do you guys see this? Alright. If you have this, please follow along. If you don't, sucks to be you. Second, 0. See how the catalog popped up? This is like Sears catalog right here. This is the math catalog. See this little A up in the top right? See that A? That means alpha. It's prompting you to type in a letter. Let's type in L. Where's the L? Oh, it's the right bracket there. L. Now I'm on the L's in the catalog. Scroll down to LCM. Hit enter. What were the numbers again for the one we just did? So 126, hit the comma, which is above the 7, and then 441. Then hit enter. 882. So boys and girls, this only works if you have 2 numbers. Alright, so the calculator will only do this if it's got 2 numbers. Okay, go back into the catalog. Second 0. This time hit G. Where's the G? Oh, it's the tan button. Now scroll down 1. See GCD? GCD? That's greatest common factor. Greatest common divisor. Can you scroll back a page? What was one of the ones we did that had 2? Scroll back a couple pages. 90, comma, 225, 45. Okay? So, if the problem has only two numbers, you can cheat with this calculator. If it has more than two numbers, you need to do it by hand with the division table. All right. Back into this booklet. Let's scroll forward. Let's do these hard numbers here. Okay? Class example 8. Make sure you have one of these in your hand. Calculator. All right. So 6912. We're going to put the division table on there. You got the calculator handy. Now we start dividing. 6912. What does it divide by? If it's even, start with 2. So everybody's trying this. 6912 divided by 2 is? Okay, it's still even. Divide by 2 again. 1728. Where's Kiki? 1728. I know this one. 1728. Isn't that the cube of 12? 1728. Oh my gosh. Anyways, let's keep going. 2 divide by 2. I got 864. Divide by 2 again. That's class example 8, Phelan. Oh, keep dividing by 2 here. It will eventually. Okay, 27, we have to switch gears. 2 is not going to work anymore. Now we can work with 3. Then you get 9, do 3 again. Then you get 3 again, do 3 again, then you get 1. So we have all the primes out to the left. Now what's the question asking us? Is it a perfect cube? So what do we do for cube? We got to put it into triplets. 3, 6. Oh, there's a problem here. Why is it not a perfect cube? It doesn't fit. Very nice. These guys screw it up. Now, go ahead and try this now in your calculator. Cube root of 6912. Okay? Cube root of 6912, 19.04881262 dot dot dot. This belongs to which number system? This belongs to which number system? Irrational. Because the decimal is non-terminating, non-repeating. Do this before you go home or before you leave class. And this assignment, you don't have to do them all, but I want you to try at least some. The answers are at the very back. Okay? Don't forget about the other homework in the regular workbook.